We want to look at how to find the volume of the solid on the right, which I'm going to remind you how that solid was constructed. We took the region R, which is the region bounded by y equal the square root of x and y equal x squared. And that region becomes the base of this solid on the right. And basically what we have is the cross sections perpendicular to the x-axis for this 3D solid are squares. Now, in the sense of constructing this 3D solid, what I want you to imagine is you're basically putting in square tiles. And these square tiles have a thickness to them. And you're basically placing these square tiles perpendicular to the x-axis in region R to form this solid. Okay. And if I rotate this, then you can kind of tell that's basically what we're doing right here. We've got each of these, in a sense, if it looks like line segments that would be placed in region R perpendicular to the x-axis are really not line segments. That's a side of our square tile. Each of these square tiles that's helping to form this 3D solid. And again, as we put more tiles in, then we completely form this solid. Now the key to finding the volume is to just find the volume of one piece. So if I can describe the volume of that one piece right there, I know with calculus I can use integration to add up infinitely many volumes of solids just like that. So obviously there are infinitely many square tiles that can go in region R perpendicular to the x-axis, and I can use integration to add up the volumes of all of those pieces and find the volume of the solid. So to show you how we're going to do that, we're going to switch over to a screen where hopefully I can write and you can see it. But we're going to take y equal x squared, that function, and y equal the square root of x, which formed our region R right here. So here's region R. And what we want to do is think about describing the edge of our square cross section. Okay, so I'm going to use a different color here. We're going to pick a point on each of these curves. And think about when we name those points, we can't call both of those arbitrary points x comma y because they both have the same x value, but their y values are different. So this point we're going to call x comma square root of x, and this point will be x comma x squared. And I'm very interested in knowing what this distance is, and we know that the distance between 2 points on a vertical line is the top y value minus the bottom y value. So that's going to be square root of x minus x squared. And I want you to think about, in a sense, that's the edge of this square tile that's put in region R to form this solid, but I want you to think about that having a thickness. So if I give that a thickness, that thickness is going to be some arbitrary change in x, which we'll call dx. So I want you to think about the idea of the fact that if I go back and look at this figure here, that what I have is this square tile that's placed in region R and placed in such a way that the square tile is perpendicular to the x-axis. And if I can describe the volume of that one piece right there, then I can integrate to add up infinitely many volumes just like it. So this is what we're going to do. We're going to go back over here to our whiteboard, and I want you to think about that cross section actually is a square tile, and that square tile looks something like this. Okay, and again, if you think about, if I just were to draw a square, we know this segment up here that's represented by the square root of x minus x squared is basically each side of that square. And again, if I go back and look at this figure here, okay, when I rotate it this way, then basically this vertical segment that you see in region R, over here on the left, corresponds really to the base of that square tile that we're putting in region R perpendicular to the x-axis. Okay, what you learn from geometry is then if I have this tile where this is square root of x minus x squared, this dimension is square root of x minus x squared, and this other dimension right here is a change in x, then I know the volume is going to be the area of the base times the height. We learned that in geometry about a prism. If the base on top and bottom are the same, we know the volume is the area of the base times the height. For these particular problems, I want you to learn it in the sense of the base is going to be the cross section. So it's going to be the area of the cross section. And the height is going to be that thickness that we gave, which is either going to be a dy or dx. On this particular problem, it's going to be a change in x. So for our problem, the area of the cross section, okay, the area of the cross section is right here, and that's going to be side squared, or length times width, so that's going to be the square root of x minus x squared squared. The thickness is going to be this change in x, but that's just the volume of that one piece. When I go back to this diagram and look at it, we're talking only about the volume of this one square tile we have on the right. And what we want to do is use integration to add up infinitely many volumes like that. So what we're going to do is we're going to integrate the square root of x minus x squared squared with respect to x from, oh, we don't have limits of integration. Now, it was already marked on your diagram, but we need to talk about how to find it. I need to know the limits of integration here for this particular problem, meaning I need to know these points of intersection. Because if I have a dx in the problem, I know my limits of integration go on the x-axis. So I need to know where the square root of x is equal to x squared. Where do those two functions intersect? If we square both sides, we get this equation that x is equal to x to the fourth. And if we set it equal to 0 and factor out an x, we're going to end up with x being 0 or x cubed minus 1 being 0, which is going to give us these two values. Now, since we squared both sides, we need to check solutions. Actually, if you go back, both those solutions work in the equation, this equation. And so we know this is 0 and this is 1. And so our limits of integration on this problem, since it has a dx, our original region R goes from 0 to 1 on the x-axis. And what I'd like you to do is get your calculator out. We'll just use the calculator to do the integral. I need you to type in the integral of square root of x minus x squared, that quantity squared with respect to x from 0 to 1. When you do, you should get approximately 0.129 cubic units. Okay, so that's our first example. We'll come back and in another video look at the second and the third examples and go from there.